Okay, let's look over the practice exam for Module D. And so first when we look at, the types of problems that we're going to see. So we have some evaluating an exponential function, finding the final amount, so using an exponential function. Then finding initial amounts typically have to do with, and rates of change. Those typically involve logarithms. But okay. Writing exponential function models of the world, converting between natural log and exponential, basic properties of logs. Um, and so what I want you to notice is there's actually, aside from like question 8, um, these are all very similar to the worksheets that I had to do this past couple weeks. And they're all about using the exponential function to model exponential growth and decay, and then using logarithms to solve for certain features when we have that model. And these are the types of things that are most common to show up in like science and finance and stuff like that. So, students in this class who need this class for their major, this is the most likely way that this will show up in your future. So having said that, let's go ahead and jump in. So the first type of question, now we have something like this. So this is an exponential model. Exponential models always look like they'll have some initial amount. And so in this case, that's the 3,900. And it's a little confusing because I used capital A for amount and they have A of t. That's because the amount depends on how much time has gone by. So I should really say this is A at 0. This is the initial amount. If you plug in 0 for t, you'll get 3,900 if you work it all out. Um, and okay, fine. And here's just as simple as to get this answer for how long after 7 hours. We just need to evaluate A of 7, and you can use a calculator for that. It's no big deal. But we have our 3,900, 1/2 to the 7 over 14 power, which is 3,900, 1/2 to the 1/2 power. Which, and again, at this point, you could use a calculator. Really, at any point, you could use a calculator. Um, but that's the same thing as the square root, which turns out to be the same thing as 1 over root 2, and this ends up being the same thing as 3,900 over the square root of 2. Now, do we round? It says round your final answer to the nearest gram. So yeah, we would round. Um, anyway, I'd use a calculator for that and then enter my answer there. And then the same idea for 40, but now instead of a 7, it would be a 40. So, okay, fine. Those are those types of problems. No big deal. How do I get... I don't like... Why is that showing up? How do I get... There we go. That's what I wanted because I need to get back here. All right, fine. So second type of problem, finding the final amount. So here we are. Okay. The city has a population of 380,000 people. And each year the population grows by 4.25%, better known as 0.0425, as if it was just a number. What will the population be after 5 years? So the idea is there's the amount that you start with, and after 1 year, you'll have everything plus the amount that you grew by. And if you just did this one time, and that would be how much is after 1 year. And then it turns out each time you sort of multiply by this amount, which, okay, plus blah, 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 I could just write that as 1.0425. It turns out that each time I multiply this by, it's like another year going by. You have the amount for the previous year plus the gain. And if that's confusing, please check out my other video going over last week's worksheet. So the worksheet on 421. Okay. Um, uh, but yes, this is the, well, whatever. So we have 3,800, or sorry, 380,000, sorry. And we need to multiply it by 1.0425 to the 5th power. So this will give us our answer, but then we want to round to the nearest whole number. I don't know, maybe I'll just do this one because why not? 380,123. And now I have 1 point. I hate how spammy this website is. Just close that, close that. Fine. 1.0425. And this is getting raised to the 5th power. Here we go. And if I round to the nearest whole number, let's actually double check. Do I just round up or do I do the nearest whole number? I don't know. Da da da. Let's see. Oops. Let's see what this says. It says nearest. Okay, so the nearest 46791. 46791. Okay. Way. Check that. Incorrect. 46791 We got that percentage. Suppose each year grows by that much. What will the population be after 5 years? We have an initial amount there. Oh yeah, there's definitely I definitely copied this wrong. So I should have caught this as a red flag. How can my population grow, but yet I shrunk? That doesn't make sense. I definitely made a mistake. Right? Let's see what happened. And you see I'm missing a zero. All right, if I go up here, um, not quite enough zeros. There's only three, so I need to insert another zero. Let's go ahead and hit that. There we go, much better. Which of course multiplying by 10 just multiplies by 10. So I should include another one on this. So one there. Now we recheck it. Oh, but then there was a rounding error probably. Let's see. Am I not being careful? Yep, now it's a 0.7. Okay, so 0.7 rounds up to a 2. There we go. Oof, man. So hopefully y'all learn from my mistakes and you see, okay, we should make sure we enter the correct amount of zeros and make sure instead of just mindly copying, we actually round and all that stuff. Okay, fine. Finding the initial amount. Sure, let's take a peek at that. So suppose the dollar value of a certain car is given by the following formula. Okay, fine. And so by the way, what's this formula saying? It's saying that the car originally cost $21,300, and every year that goes by, it's only worth 81% of what it was the previous year. So what's the initial value of the car? It's this. This is the initial value. That's going to be this first entry here. This is a decay, and so this number, 0.81, but whatever number shows up there, if I call it B for base, okay, if B is less than 1, that's decay. If B is bigger than 1, that's growth. Okay. By what percentage does a car change each year? Okay, so to not change, so if B was equal to 1, this would just be constant. It's not going up, it's not going down. 1 to the t is always 1, right? So if this value is just 1, it would stay the same. So we need to, so the percentage change is how far away from 1 we are. So 1 minus 0.81 is 0.19. That's 19%. Okay. So that should be how that one works. There you go. Let's try another, because hopefully we'll get, so that's still 0.84, so that's still decay. Let's try another, see if we can get something that has growth. I just want to make sure that, we'll see if they have different types. Why are you not loading? I'm interacting. 0.81, 0.87, 0.94. Looks like it's going to be decay. Oh, there's a growth one, right? So we have a B that's bigger than 1 happening. Fine. And still, what's the percent change each year? I would just do 1 minus 1.037. This is 0.037 or 3.7%. Okay. So, all right, that's how to do those. No big deal. Write an equation that models exponential growth through decay. Let's get that up. Okay. At noon, to begin a study, a petri dish had 2,100 bacteria cells, and each hour the number of cells increased by 11%. So this is 1 plus 0.11, but we would never really write it like that. We'd write it as just 1.11 to the t, and where t is measured in hours because each hour it increases by 11%. Let y be the number of bacteria, write a function. Okay, so this is the function that we're going to put down. So that's our answer. Okay, it's so what did I do? I had the initial amount, which I'll call a subscript 0. Then I have 1 plus the rate. So this was 1 plus 0.11. And this was 2,100. And then it's raised to the t. Okay, so that's pretty much it for that. Should we? Yeah, sure. Let's just go ahead and write this down. Write an exponential function, show the relationship between y and t. Okay, so it says show the relationship between y and t. Right, so is that right here? Oh, whatever. So I should have the letters y and the letter t show up. So I have y is equal to 2,100, 1.11 to the t. And that should do it. There we go. Okay. All right. Converting between natural logarithm. So this whole idea, now it says if you read the blue header, right, converting between natural logarithm and exponential equation. So this is about log base e, which is called a natural log, um, and an e here. And there's a relationship. So um, the natural log of x equals y is the same thing as if I were to write e to the y is equal to x. And there's nothing special about x and y. The natural log of whatever you put here, I'll put an a, equals b, means e to the that power b is equal to a. So if I'm curious, e to what power is equal to 4? Well, if I rewrite this, you can see that b is my question mark. It's the thing I don't know. But 4, that's my a. So this is like saying natural log of 4 is equal to what? Oh, and in this form, it's very clear. You just put natural log of 4 in your calculator, right? In this form, it's less clear, right? Um, but okay, so this is what we want to utilize. So we have e to the 3 is equal to y. Okay, so what's the logarithm form? So the logarithm form is that the natural log of y is equal to 3. So that's what I would put right here. Natural log, why aren't you typing ln? Maybe I have to hit the button. Fine. Ln of, nope, y is equal to 3. Right? That's what we put there. Okay, fine. I have ln of x is equal to 2. So what this means is if you raise e to the power of 2, you will get x. So that's going to be the exponential equation that goes down here. So, all right, that's how to do that stuff. How do I get... I wish I knew what all these little, like, pop-ups down here do. Ugh, I hate all this. What is happening? I changed stuff. Way. There we go. Cool. All right. Basic properties of logarithms. I suspect this one will be the odd one out. So, uh, right. Okay. So I just talked about natural log and e. In general, the log with base b of a is equal to something. Okay, c. Why not? Let's make it look more like a c. It's hard to rewrite this. What this means is that the base raised to the power of c is equal to a. Okay, fine. It can be a little confusing. The natural log form suppresses the base, and so it looks like ln of a equals c, and that means e to the c is equal to a. But all that's happening here is that we know that the base is e, and so we just don't bother to write it, but same idea. Okay, here's the thing. B to the n times b to the m is equal to b to the n plus m. And maybe that's equal to some number. Maybe it's equal to a. I don't know. Okay. But now, what all of this is saying is actually two different equations. It's saying b to the n times b to the m is equal to a, if I just look from the very left to the very right. But if I look from the middle over to the right, it's saying b to the n plus m is equal to a. Okay, fine. Now if I convert this to log form, this says log of a product. It says log base b of, oh, how do we do this? How do we do this? I need to take the log of both sides. Oh, all right, let me work backwards from what I want to say. What I want to say is that log base b of something plus log base b of something else, so we have a Nancy and a Mary, is the same thing as if you do log base b of the product n times m. And getting a phone call. I'm going to pause this recording. Indeed, I do. Let's. Okay, and we're back. And I realized during that I had poor notation. What I wanted to say, so let's fix this. I should have written this down as a product, right? So b to the n is a number. Okay. Oh, in fact, let's just make all of this consistent. Let's just redo it here. So let's start with what we want, right? And what I want to tell you, if I look at this first equation in here, it says log base 4 of 5 minus, okay, let's look at the second equation. We'll do addition first, then subtraction, right? Log base 5 of something plus log base 5 of 7 is equal to log base 5 of 14. And so the way logarithms behave, it comes from how exponents behave. And if I have log base 5 of a and log base 5 of b, that's equal to log base 5 of a times b. And so now we can see, oh, okay, if b is 7 and a times b is 14, better known as 2 times 7, then I guess this missing number must be 2. And so 2 is what's going to go right in here, okay? Now, why is this the case? Well, what is log base 5 of a? It's some number that would be the exponent that would satisfy the following. It would satisfy 5 to the x is equal to a. And what is, so in other words, I'm saying x is what I'm calling log base 5 of a, okay? And let's call y log base 5 of b. So x plus y, if I made that the exponent on 5, that's like 5 to the x times 5 to the y. And it turns out that's like a times b. And so this is the thing where when you plug it in, what is the log of this? It's the power on 5 that gets you a times b. Anyway, you can always look up rules of logarithms. There's going to be much better videos than what I'm trying to do off the cuff right here. But here's what you need to know. So I wrote this down with 5. You could have written it down with, okay, b is sort of a bad choice because I'll use b for the base. We'll do log base b of x plus log base b of y is equal to log base b of xy. So we have this sort of addition on the outside becomes multiplication on the inside. And if you did, we'll look at the last one next. Okay, so log base b of x. And if there was some number out here, so some number a, okay, so a times log base b of x, that's equal to log base b of x to the 8th power. And a special case of this is when you have a negative logarithm. Negative log of x is equal to log base b of x to the negative 1, right? Because that's really a negative 1 right there. And that's the same as log base b of 1 over x. And so now, if I were to write log base b of y minus log base b of x, you could think of this as log base b of y plus log base b of 1 over x, because of this monstrosity became that one. But now I have a plus. And so I can use this rule up here, and I multiply the two things on the inside, and y times 1 over x is the same thing as y over x. So what I get is log base b of y over x. And so that's the subtraction rule. So anyway, putting it all together, here we have a 2. Here I want to think of 5 divided by 9. Okay. And here, this is going to be a 2, because what I'm using is that 2 to the minus 5 power is equal to 1 over 2 to the 5th power, which is equal to 1 over 32. Okay. Anyway, I imagine this will be the problem that will sort of separate the A and B students, so to speak. It'll separate those who get all 10 questions correct, and this will probably be the most common missed problem, or something like it, right? So, okay. And again, for perspective, right? Perspective is always nice. How do we get out of this freaking thing, man? Okay, cool. That is one question of all these practice questions, and it sort of stands out. This is sort of like the pure math side, and then all the others are sort of modeling and applied type stuff. So let's take a peek at this type of question. The number of bacteria in a certain population increases according to the following function, where H is measured in hours. Okay, fine. How many hours will it take for the number of bacteria to reach 3,800? All right, let's get ourselves more room. And the problem asks how many hours. So we're solving for an exponent. So we know logarithms are going to have to show up. We want to reach 3,800. So that's what the output's going to be. The input is our function e to the point, I missed the 0, 08h. Okay. And so now we need to solve for h. So I want to get this exponent. So I need to sort of strip away these layers to get there. So I'm going to divide both sides by 2,900. Those will cancel. So now that's gone. Let's do a medium size. Oops. Okay. So now I have this. And at this stage, if I now take the natural log of both sides, natural log of this is equal to natural log of that, then over here it stays the same. I have natural log 3,800 over 2,900. And it's kind of gross, but whatever. And over here, if you have a natural log and an e, they're inverse functions, so they undo each other. If you remember, f after f inverse of x, it's just x. And so what happens is just the exponent lives on. Sort of what's happening is x is equal to 0.08h. So I have my e to the x and then ln, and then these sort of undo and you just get x. Okay, so now we need to solve for h. And so now we can see that h is going to be what happens when you take all this stuff, 900, and you divide it by 0.08. Okay, so put this in your calculator, round to the nearest tenth, and then there you go. Okay. All right, so that was 9, almost done. All right, so finding these are all in your this week's worksheet, these types of questions. You get more practice with it. Okay, so we have y equals the initial amount, e to the minus 0.072t. We need to find the half-life. So the initial amount, whatever it is, maybe it's 100 grams, maybe it's a kilogram, maybe it's a ton, right? Who knows? Who cares? But some amount of time goes by. And because this is a negative, this is actually like y0 divided by e to the 0.072t. But the point is that as t increases, you're going to get smaller and smaller things out on the side. This is a exponential decay function. And we want to know when y is 1/2 y0. When does that happen? And well, okay, what's y equal to? Y is equal to this monstrosity. So this is when you can get rid of that, and you can set 1/2 y0 equal to y0 e to the minus 0.072t, right? Because I have two different forms for y. So one form for y is this. The other form for y is that. And so you can sort of set these two y's equal and instead just notice that this is equal to that. And so that's what I'm doing over here. Okay. Anyway, so we focus our attention on this equation and notice, oh, the y0's cancel. You can divide them away. And what really matters is just when does our exponential part equal a half? And that's what a half-life is. And so what do? We take the natural log of both sides. This is equal to natural log of that. And so we get natural log of 1/2 is equal to the exponent itself. So negative 0.072t. So I need to divide that over. So I have natural log of 1/2 divided by negative 0.072. That's going to be t. That's what we want right there. And so punch in the calculator, and then we need to round to whatever it says, nearest tenth. Okay, fine. All right. Write an evaluated function. Sure, why not? Let's do it. Okay, area covered by population of bacteria. Sure. The initial area is 3.9. And it follows a continuous exponential growth model. It says it in italics right there. And so that's the initial amount, exponential kt. So I have exponential kt. And so this is going to be our amount function. Amount is a function of time. Okay. And okay, see, they're already giving us that form there. Oh, I must have messed something up. Wait, it has an initial area of 3.9 and it has a doubling time of 8 days. Okay, so this value here, the multiplier to our initial amount, that multiplier will exactly equal 2 after 8 days. T is 8. So K is equal to the natural log of 2 divided by 8. If getting from here to here is confusing, then that tells me that you need to practice more of what the other problems were. So how do we get from there to there? We first take the natural log of both sides. So I have a natural log of 2 is equal to the natural log of e to the k times 8. These two things cancel, and you'll get, I guess there's one more step. You'll get natural log of 2 is equal to k times 8, and then you divide the 8. So then you'll end up here. Right? Okay, so now we have our function. It's 3.9 e to the natural log of 2 divided by 8 times t, right? So this whole thing is the exponent, and k is this expression here. Now we can clean this up, but we're encouraged to leave it in base e, so I'm going to go ahead and leave it like that. And it says use exact expressions, do not approximate. So when we write this, we need to write 3.9 up here. We need to write natural log of 2 over 8. Okay. So let's go ahead and also, this is so annoying. Go away, go away. Let's go ahead and just take a look at the natural log of 2 divided by 8. Okay, there we go. So if instead of writing that, if you would write like 0.0866 or whatever, you get marked as wrong. So don't do that. I'm going to store the idea of natural log of 2 over 8 as the value a. So it looked, if I kept writing this for as many digits of precision as the calculator allows, that's what's stored in the value a. So now when it comes time to actually compute stuff, I can do 3.9 times e to the, and then this is now just the letter a. And in the problem statement, we want 14 days to go by, so I'm going to plug in 14 here. A times 14. Will it like that? I don't know. Let's just be safe. 14. There you go. Okay, so after 14 days, I have 13.1179. And so now when I go back here, it says round to the nearest tenth. So I have 13 point, it was 1, so there's the nearest tenth. Let's go ahead and check that. Okay, there you go. So notice how on the first part, you have to leave it as natural log of 2 divided by 8. On the second part, punch the whole thing in your calculator, where I'm plugging in 14 for t, and you can round all that. So no big deal. All right, last question. It's going to be the same kind of idea. All right, so this time, so on the last time they told us the doubling time, right? And we had to solve like 2 is equal to e to the kt. And oh no, we'd have to plug in t, and it was 8. Remember that last time? So this time around, we don't get a doubling time. We get sort of a more general idea. We sort of know 2 different snapshots. So to begin the experiment, the initial amount was 400. Okay, so we have 400 e to the kt. This is our general form. And after 18 hours, so 400 e to the k times 18, we have 260 kilograms. So now we can solve for k, right? So what's going to have to happen is you divide the 400 over, and then you take the natural log of both sides, and you'd have to divide over the 18. So this monster here is k, okay? And if that was confusing, go back, look at how we solved this, and realize it's all the exact same steps, just a little bit worse numbers. Okay, so that's k. So that's what's going to go where my cursor is currently blinking over here. I would type in natural log of 260 divided by 400, and all of that is over 18. 400 is the amount out front, so that's going to go over here. And then once you have all that done, plug in 19. So, okay, so now what does our function look like? Our function looks like 400 e to the, and then this thing. So ln of 260 over 400 divided by 18, my God, times t. Okay, so all of this is the exponent. And if you plug in 19 for the hours, then whatever you get, you're going to round and punch it in there. So, okay, that is your practice exam. Hopefully this all helps. And that's pretty much it for the semester.